Hello, welcome to MAT 223 Engineering Mathematics class. In this lecture, we will learn solution by substitution. We will employ substitution idea to solve several different equation types. Our first equation type will be homogeneous equations. The second will be Bernoulli's equation, and then we will learn reduction to separation of variable using substitution. Okay, so first start with homogeneous equations. A definition: if a function f satisfies f of tx comma ty is equal to t to the alpha f of x comma y. This is basically if you multiply the components, the inputs by t, it means the output will be multiplied by t to the alpha in front of the original inputs. Okay, then we say this f function is a homogeneous function of degree alpha. Okay, this degree alpha comes from the power of t. Now an example: f of x comma y is equal to x squared plus y squared is a homogeneous function or homogeneous equation of degree 2, because if you substitute t x and ty for x and y respectively, we will end up with tx squared minus ty squared. And as you know, this t squareds can be come out, and we can rewrite this equation as t squared times x squared plus y squared, and x squared plus y squared is the original function, right? F of x comma y, so we substitute it there, and this will be basically meaning we started with t times the inputs, and we end up with t squared times the original inputs at the function value at the original input. So this means we have a homogeneous function or homogeneous equation. We can say function. It sounds better, and this its degree is basically equal to 2 because we raise the power 2 on t. Okay, so this is an example. A definition: a first order differential equation dy dx is equal to f of x comma y is homogeneous equation if the right hand side function, this f, is homogeneous of degree 0. Okay, so this function has to be a homogeneous function and degree has to be 0. Okay, so degree being 0 means f of tx comma ty is equal to f of x comma y, because this will mean the degree 0 means t to the 0 power, and it's basically 1. Okay, so this means we can multiply the inputs by t and it will not change the function at all. Okay, so it will give the exact same answer as if you put x comma y as your input values. Okay, so for this particular differential equations, like homogeneous equation in this form, we substitute y is equal to ux. Okay, so this is the key point: y is equal to ux, and this u is a function of x, and this will reduce our differential equation to be a separable one. Okay, so our differential equation will be separable equation after substituting y is equal to ux. Okay, so let's do it in general. For example, if we have this sort of homogeneous differential equation and we substitute y is equal to ux, then this requires finding dy dx and f of x comma y in terms of u and x. Okay, so in this form it's in terms of x comma y, but we need to substitute u instead, so it means we need to find everything with respect to u and x. Okay, so to do that we start with dy dx. Okay, if we take the derivative, x derivative on this equation, we'll have dy dx on the left hand side, and on the right hand side this will be the derivative of product, x derivative of the product. So the x derivative of product will be basically equal to the derivative of x times u okay, plus derivative of u times x, okay. So this is basically the product rule. Now we have an expression for dy dx in terms of x comma y, u, okay. So we replace dy dx by u plus x times du dx, okay. This is the first thing we have to do. So left hand side is already there, and let's go with the right hand side. Then f of x comma y is basically equal to f of x comma ux, okay, because we substitute ux for y. When we do that, if you see, these x are common on both components, on both input values, okay. So if we take this x out, it will be x to the 0 power, right? Because this is a homogeneous differential equation. For this reason, f has to be a homogeneous function of degree 0. Then this means any common product can come out with 0 power, okay. So x is common component coefficients on both terms, so it can come out as x to the 0 power. And here in the first component we will have 1, and in the second we will have u, okay. So this is what we end up with, and this is basically equal to x to the 0 will be 1, and we will end up with f of 1 comma u, okay. So this is the second part. Now we are ready to rewrite the differential equation in terms of u and x, okay. On the left hand side we have the dy dx, and it is basically here. We found it here on this part, and we have f of x comma y, and f of x comma y is equal to f of 1 comma u, because we have found it this way, okay. So if you move u to the other side and divide everything by x, we will end up with this expression, and then this expression can be rewritten as f of 1 comma u minus u times 1 over x, okay. So this is a function of u, okay, all alone, and this is a function of x alone. So this means we have a separable equation, okay. So because this is a function of u alone, and this is a function of x alone, if we can write the right hand side as a product of the first parameter times for the function of first parameter times the function of second parameter, then we say it is a separable differential equation. Okay, let's solve an example. There is a differential equation given here. We first need to observe this homogeneous differential equation. So this is a homogeneous differential equation because if you substitute ty for y and tx for x, we'll end up with t squared here, t squared y squared here, and t squared x squared there. T squareds are common, so we take t squared parentheses here, and we will end up with t squared y squared minus x squared. On the bottom we have tx times ty, and this is basically equal to t squared times x comma y, and x times y. So t squares are common, so we cancel them out, and we will end up with the original right hand side. So this is really a homogeneous function, okay. So now we need to perform a y is equal to ux substitution. This is to rewrite the differential equation as u plus x times du dx, because this is from the previous observation, right? Whenever we substitute y is equal to ux, the right hand the derivative dy dx will be equal to u plus x times du dx, okay. So this is what we really have, and on the right hand side we will put ux for y, okay. So this will be ux squared minus x squared divided by x times ux, okay. Now we see u squared x squared here minus x squared, and also x squared u here, okay. X squareds are common, so we cancel them out, and we will end up with u squared minus 1 divided by u, okay. So this is basically equal to u minus 1 over u, Okay, this is just a simple division. Okay, so it follows from the last equality that x times, because u's are common on both sides. Okay, so if you, let's use a pen. So this is our left hand side and this is our right hand side. That's also okay, let's make it a little bit smaller. Okay, so this is our left hand side and this is our right hand side. So u's are common on both sides, so we cancel them out and we will end up with x du dx is equal to negative 1 over u. Okay, so this is our new differential equation and this u is our new unknown. Okay, so now we, after some simple algebraic manipulations, we'll see this is equal to u du integrated and dx over x integrated, and on the left hand side we have u squared divided by 2. On the right hand side we have negative ln x plus some constant. Okay, if we back substitute u is equal to y over x, because u is basically equal to y over x. Okay, if you substitute this quantity in this what expression in the last solution we found, so here this will give us y squared is equal to x squared times c minus ln x squared. This squared comes from these two multiplied uh, to the right hand side, so we'll have negative 2 ln x. So negative 2 ln x means negative ln x squared, because 2 can be rewritten as the power of the input of the logarithmic function. Okay, so this is what we really end up with, and this is our solution to the differential equation. You can check if this is really a true solution, so you basically need to substitute this solution in the differential equation and see if you can really get an identity or uh, something like 0 equals 0. Okay, so Bernoulli's equation, first order differential equation of the following form, said to be Bernoulli's equation if it is in this form. Okay, this looks similar to the linear equation if this wasn't here. Okay, so y to the n power breaks the linearity. Okay, so if this was not here, then we could say, okay, this is just a linear equation, but this y to the n makes it Bernoulli equation. Okay, so px and qx are two continuous functions on some interval on which we seek the solution. Okay, n is a real number. It's like maybe 1, 2, 5. Okay, but if this is just 1, then it doesn't make sense to call it Bernoulli equation, because if it is 1, we can basically move this to the left hand side and combine this with this term and say this is a separable equation and solve it this way. Okay, if this was 0, then it would be linear equation. So for this reason we assume n is not 0 or 1. Okay, otherwise it's already simple enough to solve. Okay, so substituting u is equal to y to the 1 minus n. N is not equal to 1, right? Because if it is 1, then we say it's separable equation, so it's simple enough. So n is not equal to 1, so this is basically u is equal to y to the 1 minus n. Makes sense. Okay, so this u is also a new dependent variable, and this new substitution, the substitution will reduce our Bernoulli equation to a first order linear differential equation. Okay, so to illustrate this, consider the Bernoulli equation here. Okay, so when you substitute u is equal to y to the 1 minus n, this requires finding dy dx in terms of u and x. And this will be basically, if you take the derivative on both sides, this will be du dx is equal to the derivative, x derivative of the right hand side, and here we have a power function and it is y, so we need to apply chain rule. Okay, so we will end up with 1 minus n times y to the negative n, because we subtract 1 from the power, and this will be basically y to the negative n, and then dy dx, because we are working with y, and by the chain rule this requires the derivative of inside, so dy dx will come out using our chain rule idea. Okay, so then if we solve this expression for dy dx, then we will end up with this expression. Okay, so it means for dy dx we need to substitute this expression here. Okay, so this is there, and also px y will remain as is, and qx y will remain there. I could also eliminate this y to the n, and I'll use something with respect to u, okay, some term with u, but I didn't do that because at the end of the day this y to the n's will cancel out, so I just don't want to confuse you, and this will already go away. Okay, now if we divide everything, all the terms here, by y to the n, we will have this function. It is basically 1 over 1 minus n, because y to the n will go away, du dx, plus px times y to the 1 minus n, because we divide by n, and it means y to the 1 minus n. Okay, and here y to the n will go away, and we will end up with qx. Okay, so you need to recognize that this is our u. Okay, so y to the 1 minus n is basically equal to u. Okay, so this means we can replace this guy by u, and doing so will give us this differential equation. Okay, so this differential equation is really a linear equation for u. Okay, so this is du dx and some constant here, just a number here, and then px, the function of x, times u equals qx, and there is no u here. Okay, so this means we have a linear differential equation for u. Okay, so this linear differential equation can be solved using our integrating factor idea. This is basically e to the integral px dx, and if you multiply both sides by that, you know what to do with linear equations. Okay, so I just leave it alone at this point. Okay, so an example: solve the following differential equation. This is dy dx is equal to dy dx plus y over x is equal to xy squared. Okay, so this is a Bernoulli equation because we have dy dx here plus y, this px times px is equal to 1 over x. Okay, 1 over x times y, and here we have x times y squared, and qx will be x. Okay, so this is basically a Bernoulli equation with px is equal to 1 over x, qx is equal to x, and n is equal to 2 because the power of y is equal to 2. Now we substitute u is equal to y to the 1 minus n. Y to the 1 minus n will be equal to y to the 1 minus 2 because n is 2, and this will be basically equal to y to the negative 1. Okay, so we basically substitute u is equal to y to the negative 1. Okay, when we do that, we need to take the derivative on both sides. This will be du dx is equal to negative y to the negative 2 dy dx by the chain rule and the derivative of power function. Okay, so this will be our du dx. If you solve this for dy dx, we end up with this term. Okay, dy dx is equal to negative y squared du dx. Okay, let's substitute this in the differential equation. When we do that, we will see this is the dy dx part because we have found it this way, and then y over x will remain as itself, and xy squared will be the same. Okay, so if we divide everything by y squared, we will have negative du dx plus y to the negative 1 over x equals x. Now y to the negative 1 is u for us. Okay, so we replace this term by u, and this will be our new differential equation. Okay, this is a linear differential equation, and for this linear differential equation, it's already in the standard form. Our px, not this px, this is the new px for the linear differential equation. Our px will be -1 over x. Okay, so if we find an integrating factor, mu x will be equal to e to the integral -dx over x, and this will be e to the negative ln x, and this will be basically 1 over x. Okay, so if you multiply the differential equation, this differential equation, through the integrating factor 1 over x, then we will have this differential equation. Okay, so this differential equation on the left hand side is equal to the derivative of this product, u times the integration factor. Okay, and on the right hand side we have -1. Okay, so the derivative is equal to -1 means itself is equal to -x plus c. Okay, so this is what we really have, and then if you multiply both sides by x, we will end up with u is equal to -x squared plus cx. Okay, now u is this, but we know we need to return to y values, and y is basically equal to 1 over u, right? Because from here we say u is equal to 1 over y, and y is equal to 1 over u. So if you substitute u here, you will see our equation will be, our solution will be this function. Okay, so this is basically 1 over this guy. Alright, this is our solution. And this completes our discussion with Bernoulli's equation, and we will next see the reduction to separation of variables in some particular functions. For example, particular differential equations. For example, if we have this sort of differential equations, for example, on the right hand side we have ax plus by plus some constant. Okay, so it will be a function of this guy. Okay, we will see this guy on the equation all the time. So x will not come separated, or y will not appear separated. It will be always with always with these terms all the time. Okay, or some function of these terms. Okay, so now if we set u is equal to the inside the function, so u will be equal to ax plus by plus c, and we assume b is non-zero. Okay, so if we take the x derivative, it will be du dx is equal to a plus b times dy dx, and c will go away because it is just a constant. Okay, so if we solve for dy dx, we see this is our dy dx. Okay, and then on the right hand side we have f of u, because we said this is basically equal to u. Okay, so we will have this differential equation. Okay, so if you move negative a over b to the right hand side and multiply both sides by b, we will have du over dx. Du dx is equal to bfu plus a. Okay, just recognize this is a function of u alone. Okay, this is just a function of u, and there's no x here at all, so this is the separable differential equation. Okay, this is a separable differential equation, and we know how to solve it. Now let's see it on an example. Solve the following first order differential equation. This is dy dx is equal to sine of x plus y. Okay, so this is x plus y, and on the right hand side we see a function of x plus y, so u is equal to x plus y will be our choice for substitution. And then if you take the derivative here, we will have du dx is equal to 1 plus dy dx, because the derivative of x is 1 and derivative of y is basically dy dx. Okay, so if you substitute this in the differential equation, we will see dy dx is equal to du dx minus 1. On the right hand side we have sine of u. Okay, So this is our differential equation, new differential equation. And if you move 1 to the other side and divide everything by sine u plus 1, we will see this is this, because this is separable equation, this is the integration we leading to the solution. So this is what we really have. And on the right hand side, the integration is quite simple because this will be x plus some constant. Okay, on the left hand side we need to do some manipulations and recognize what's really happening. Okay, so let's put x plus c here, and there we have 1 over cosine squared. 1 over cosine is secant, and this will be secant squared. Okay, the first component will be secant, and in the second we have sine over cosine squared. This is secant times tangent. Okay, secant times tangent u. Okay, so this is rewritten in this form, and we separate the integrals because this is, we have minus there. We are allowed to do that. Okay, so this is the derivative of tangent. We know the derivative of tangent is secant squared u, and this is the derivative of secant because derivative of secant is secant times tangent. Okay, so this is basically tangent u, and the other one is equal to secant u. So as a result, we say x plus c is equal to tangent x plus y, because we back substitute u is equal to x plus y, and this will be tangent x plus y minus secant x plus y. So this is our solution. Now, if we haven't done this substitution, this will be quite hard to solve because this sine x plus y, this doesn't look separable or linear. It's nothing really. We can maybe use some ideas like separating this sine x cosine y, like sine x cosine y plus cosine x sine y here, but this might not even lead any solution there. This will be really a tough one, but this substitution makes life quite simple, and we could solve this differential equation using this substitution, and this helped us a lot. Okay, this concludes our lecture. If you have any questions, please feel free to ask me through my email. So that's all for today. Thanks for watching and listening carefully. Bye.